All right, so asked to take a look at exercise 10.6. And so this is our parallel and series reactions in a batch reactor. And so this is analogous to back in chapter 8 when we looked at series and parallel in an isothermal CSTR. So here we have an isothermal steady state, or no, I guess just isothermal batch reactor. And what we're going to look at is we're going to look at a series and parallel case in which we play with the pre-exponential term of our second reaction. We're just going to write it out as a multiple of our first reaction. And before we go over to MATLAB, just want to point out in 10.6, so in section 10.6 in the text, you try and lay out these two cases. So parallel case will have A goes to B and A goes to C. So in all cases, it's a 1-to-1 reaction. B being my desired product. Here I have the side reaction in which A is reacting to form C. Series, my desired products participate in the second reaction to form C. And so here's my mole balance design equation for A. All right, you'd write an equivalent expression for B and C. Right, and so what's going to change for the series and parallel case would be the value of my stoichiometric coefficients, and then also my rate expressions. Okay. So our parallel reaction, our second reaction is first order in A. For series, it's first order in B. Okay, so you can take a look at the text and get all that info, but let's just go take a look at the code and see exactly what we have. Okay, so this is what I received. Let's make it big and go through it. So functions const 10.6 with an input variable of a flag. So it looks like the goal is to make x this value to multiply k0 by to get k02 in input, but it's not quite there. CA0, CBC, CB0, and CC0. 2400 seems a little big. I thought the initial concentration was 2. Okay, but that's a minor detail. Then we have this logical block here. Okay, let me tab that in. Okay, so this tells me then that flag must be some variable that's going to tell us if you want to do, say, series or parallel case. Maybe. Okay, because then you have a check that if flag is equivalent to 1 to do this. So the first thing that already stands out to me is your initial conditions for B and C are not used, right? CB0 and CC0 are they're both 0, but they're underlined in red that they're not used. So you're not using your initial condition for B and C. And then, I don't know if this is series or parallel, but what stands out to me is, you just give an initial concentration of A, and it looks like maybe you're trying to get at 3 different versions for A, B, and C. And, that's not the case. You have a system of 3 initial value ODEs that you're going to solve simultaneously, right? And so this should ultimately be a vector of CA, CB, and CC0 because you're going to need initial conditions for all 3 of those values or functions you're trying to solve for. It's a function of t. The other thing that stands out to me is this is my range of time. You're starting at point 1, right? Typically, you're always starting at 0, right? A time of 0 seconds. Where you might have point 1 in your head is when we used F0 to solve for the time at which we get a particular value. Then with F0, you couldn't start at 0 because it would result in an ODE 45 call in which you integrate from 0 to 0, which is why we typically bumped it up. Okay, but let's look at this. Okay, so par 1 or par A. So I'm looking at my rate function. Okay, again, let's untab that end statement so they're lined up. This is mostly all tabbed in. Okay, let me untab that. All right, so x1 is 0.1. So from the top, that looked like your multiple of k02 is a function of k01. So my rate expression's good. There's k02 as a multiple of k01. Calculating k2. All that seems fine. Okay. And so these are just, constants, okay, which just as well could have been defined up top and passed, but we won't worry about that quite yet. Now, okay, now here, okay, so if this is my parallel case, and I'm guessing that's based it by par A. Okay, so par A is when I have A goes to B and A goes to C. So reaction 1 and reaction 2 is first order in A. Okay, so Y then is just concentration of A, which makes sense since when you called it, you just give it initial concentration of A, right? But in theory, you want to try and solve for A, B, and C. Okay, we'll tweak that in a second. Stoichiometric coefficient of A in both cases is -1. And so, yeah, so that's in theory, okay. Okay, let's just leave that for now. Okay, I'm going to change this to 0. So without changing anything, let's just see if this animal works. Okay, yeah, so it returns the concentration of A at, in this case, 1,000. Okay, let's make this 0.1 again. All right, so 0.1, right, works. It's just, it's going to begin integrating at a time of 0.1. Okay, where Ca naught is the concentration of A at time 0, not at 0.1. Okay, okay, so this, is okay. But what if I want concentration of B and C? So if I had a single reaction, it's pretty straightforward to work out via stoichiometry. But it's a little harder for the series and parallel case. So what I want to do is I'm going to take this and I want to solve for the concentration of B and C as a function of time as well. Okay, so the first thing I'm going to do is I'm going to make my initial conditions a vector of initial conditions for A, B, and C. Okay, and then what I need to do here, okay, and my rate function, okay, is I'm going to make this big Y, okay, make it consistent with what I have up top, okay, and then I'm going to unpack Y, okay, and I'm going to make the first element concentration of A, second element the concentration of B, third element concentration of C. So the R1 and R2 can both be first order in A, or both be first order in A. Okay, cool. Okay, stoichiometric coefficients of A. Okay, you should add comments. So B. So I'll make this, so new B1, okay, reaction 1, B is a product, so that'll be a +1. Reaction 2, this is parallel, so it's not in reaction 2, so that could just be 0. Okay, so looking at C next, so C isn't in reaction 1, so that could be 0. In reaction 2, it's a product, so it's +1. Okay, and then I'm going to take this, okay, and let's just call this, res A. That's my rate expression for A. But then, B, okay, and I'm going to literally copy and paste, because when it comes to my mole balance design equation for B, right, all I need to update are the stoichiometric coefficients. Okay. Alright, so all I need to do is update this for B and C to use the appropriate stoichiometric coefficients. Right? And I like listing stoichiometric coefficients of all the species, even when it's 0, right? Because, right, it allows me to write it in this general form as I have it in the problem, so that if, my rate expression or that were to change, there's not anything I would need to change. Okay? Cool. And then what would be left, okay, and so actually let's add a comment. So here's my rate expressions, or mole balance design equations for A, B, and C. Okay, And then the last step would be to, pack up our mole balances. So res then would be res A, res B, and res C. Okay, cool. All right, so let's just take a look, and yeah, okay, and then we'll incrementally improve this and update this. Then what I want to do is just when I return this is, so when I call ODE45, T is going to be a vector of time, so it's going to be a column vector of all the times at which my functions, concentration of A, B, and C were calculated. And Y is going to be a matrix, where the row will correspond to the corresponding time. Column 1 will be concentration of A, column 2 will be concentration of B, and column 3 will be concentration of C. Okay, so if I want that final row, what I want is the last row, all columns. Okay, so just so you can look at the equivalent, or if I run this now this gives me concentration of A, right? And let's make sure it's the same. Yeah, that's 364.6214, right? It's concentration of A, but now I also have concentration of B and C, right? I have them all. All right, so if I were to play with this, okay, I'm going to go ahead and delete this. So it looks like you were trying to create a separate rate function for B and C. Okay, so I'm just going to go ahead and delete. Okay, and then let me call this, let's call this, we can call it pare, that's fine, parallel reaction. Okay, cool. And maybe instead of just returning that, okay, well, how do we want to do this? Well, the first thing I'm going to do is actually, so when I go back up here, okay, the initial number of moles is 2400, right? And I'm looking for is where do we have the volume in here? Because I want to say the inlet feed, or the inlet was 2 molar if you were to convert everything to moles. Okay. If we use moles instead of molar concentrations, it's not the end of the world. We would just need V then, because you see I have V here in my rate expression, and so the idea is that V is constant, as we assumed in the CSTR for dilute. We could factor that out, bring it over to the left-hand side, and factor it into my differential, because NA over V, or just N over V, is going to give you concentration. So looking at it just like this, I'm not seeing it, but it should be that the concentration at time equals 0 was 2, but again, I'm not seeing it. And regardless, it doesn't matter. You could just assume a basis. So you can take the concentration to be 2400, just assume a basis of 1 liter. Okay, and again, what's going to happen is if I look at my rate expressions, there is a V here because my rate expressions are typically normalized. So when I have a homogeneous bulk phase reaction, I typically normalize my rate expression with respect to volume to make it intensive. And so, ideally I should have a volume here if I'm using moles. But typically we convert to concentration, where if we assume the volume's constant, factor it out, bring it over the left-hand side. This would be 1 over V dNA dt. I could bring the 1 over V into the differential since it's constant, where NA over V is just concentration, right? And I could convert these to differentials of concentration. But I'll leave this as here. You can assume essentially a basis of a volume of 1, right? And that's fine. That's a subtlety. Okay. So if we were to go with that, let's plot our results. Okay. Now, one thing you could do that I often like to do is Y is a matrix, and I often like to unpack that as well. Okay, and I'll show you what I mean by that. Okay, so spacing just a little off. So let's unpack y. So if I look at y, the concentration of A, remember that's the first column of y, so that'll be y, all rows, column 1. Concentration of B will be y, all rows, column 2. See C, so concentration of C will be all rows, column 3. So if I want to plot the results, this might make it easier to see that. Let me do a figure 1 just in case we end up adding another one. Hold on, and then we plot T, comma, CA, and that'll be a red line, say. B will make black. I guess maybe I should just not specify colors because I'm going to run out of colors that I have that I can recall. Let's do B. I think that's blue. So my X label will be time in seconds. Y label will be so actually, we could think of it as moles if you want to assume that V is just 1 and take that as a basis, or you could think of it as concentration. It's the same. Okay, let's just say concentration. We'll use molars if we have this basis of 1 liter. Okay, and title would be right, and maybe if you get fancy for each case, you'd probably want to update this as well. Okay. But now let's see, right? And I won't, take this code to completion, but we'll put some interesting features in there. Okay. So now here's my plot of concentrations versus time for parallel. Looks like I might want to think about making time bigger. Forgot to comment that out. So let's put another 0 up here. Okay. Let's rerun it. And bam, right? So, now I'm making a cool plot, returning those final compositions. Right? Now you're asked for other things like selectivity and such, but hopefully this is enough to get you started. Okay. 2 more tricks I want to show you to think about is, I am a person that very much likes to copy and paste. Right? And so let's say I want to do series. Okay. What I would do is I'm just going to start by copying and pasting my rate expression for parallel. Okay, because all that's going to happen is my mole balance design equations, whether it's series or parallel, right, are going to be identical. What'll just change is stoichiometric coefficients and my rate expressions. Okay, so if I want to do series, right, I start by just copying my rate expression for parallel. Okay, I just pasted it. Okay, and that was pare. Let me call this maybe sure. Okay. You have the multiple in there, and however you want to handle that. Ideally, you'd make an input, and we can look at what that might look like. But this business would be the same. Okay, what's going to happen is when I have series, it's A goes to B and B goes to C. So my first reaction is first order in A, second is first order in C. Okay, again. Okay, for series reaction, what happens is my second reaction is now first order in B. Then I need to update my stoichiometric coefficients. So first reactions, A goes to B. Okay, so if I look at new A1 or V A1 VB1 VC1, that's my first reaction. So if A goes to B. Okay, and my second reaction though now it's B goes to C. Okay, so that's all I need to do. I updated my rate expression, updated my stoichiometric coefficients, and everything else is exactly the same. Okay, so maybe that's case 2. Okay, so let's do, actually, just need to carry on the logical block. We can keep that. So then maybe I want else if flag is 2, okay, series. Okay, and here this was parallel. Okay, so same old me again, and maybe even watch this. Hold on, let's let's ditch the title there. Okay, and I'm going to take my plot. Actually, I'm going to take my plot and my unpacking. Even res. Okay. Hold on, I missed something. Okay, so I'm going to take all this. So I'm just going to use the flag then to point to what rate function I use. Okay. And again, you can spice this up or change it up however you want, but just to give you an idea of how you might think about generalizing this. It's a flag 2, then I'm going to resolve the same problem, only now I'm going to use my spacing's just a little off. I'm just going to use my second rate function, which corresponds to series. All right, so now I've just set up the logical block. So if it's flag 1, it's parallel. Flag 2 is series. It's just going to dictate what rate function I use in terms of solving my diffie-q. And then I can unpack and plot and return just the same. Okay. So if this were type 1, get the same result. And we can look at ways to add titles up there. There's series, right? Cool. Cool. All right. You could even save. This is just you could save your function handle if you wanted to variable. Okay, we don't need to go that crazy, but if you wanted to, you could open up, say, figure 1 here. And we'll just have a hold on there just in case. And you could put, say, up here, title. Parallel, or down here if it's series, you could change the title to series. Okay. Right, and so now I've got series on there when it's series, when it's parallel. All right, parallel. All right, and there's a lot you could do to play with that. Okay. And have fun with that. The other thing I might think about is making that multiple input up here. So what if the user could specify X? That'd be great. Okay, then all I'm going to do is I'm going to come down to my rate functions. I'm going to make X an input. Okay, make X an input. So then all I need to do up top is let me use an anonymous function to pass X. Okay, so let's do pare final is at t comma y par a t comma y comma x. Okay, and then here use pare final. All right, well, my final rate function only have those 2 inputs, and so I'm going to pass X to pare. We do something similar to series. Again, here I am just copying and pasting. Add X as an input. Not add X as input, X is add as an input there. And then this would just be Sarah final. Okay, cool. So now I'm going to run, so this will be parallel. Let's do X is 0.1. Oh, did I make sure I commented out? Yep, commented out X, commented out X, not here. So make sure X is commented. Okay, bam. All right, and I see, it's used as an input. It's not underlined. T's underlined. That's another conversation, but that's okay. Okay, so I make X an input. Parallel case works just as before. Series works just as before. If I want to look at multiple of 10, all right, works. Series, right? Now I can just readily change that multiple, right? And you could have, as much fun as you want playing around with all that. Okay, so I'm going to leave it at that. Again, you can change this up however you want. You might think about converting your time to minutes, right? 10,000 is quite large. Do minutes or hours, whatever you want. Probably minutes. In terms of concentration, right? Again, we've assumed a basis of 1 liter. But you could go ahead and spice this up however you want. You could think about having a script that runs different cases. Maybe even in your script, you just return your entire T and Y matrix and create the plots there, so you can customize the figure headers. Or, in fact, you could even do that, from within your script, right? So as a comment, okay, so I create this, but figure 1 is still active. So let me minimize. I want to try and get it so you can see both of these. Right, so bear with me. Right, so this is figure 1, right? So I could call this function from a script with these different values of x, and then I could always just update the title. So maybe I want to update the title to series with k not 2 is equal to, what multiple did I use last time? I need to look. K not 2 is 10 times k not 1. Alright, and so if I were to have a script where I call for each of these cases, I could then just, after running it, update the title and save and print if I wanted to, right? And so that's something you can do. Also look at the problem, see the other information that it wants. Well, hopefully that gives you an idea of getting going and playing around with your code.